In this video, we review briefly the derivatives of 6 inverse trig functions. Now, these are based on this idea. If I have some curve where y is a function of x, so I have like y equals f of x, for example, I might be able to solve for x as a function of y. Now, if I'm able to solve this equation for x as a function of y, those two equations represent the same set of points. But we're just changing our perspective from thinking of y as a function of x to thinking of x as a function of y. In that case, the derivative of x, or derivative of y with respect to x, is equal to 1 divided by the derivative of x with respect to y, where that x is a function of y and that y is a function of x describe the same set of points. With that in mind, we can use that fact to compute the derivative with respect to x of the arc sine of x. Well, according to this, it's the same as 1 divided by the derivative with respect to y of sine of y. And that's the case because if arc sine of x equals y, then sine of y equals x. So this is x, the derivative of x with respect to y. You say, well, what's the derivative of sine of y with respect to y? Well, it's just cosine of y. Okay, well, I'd like my answer in terms of x, not cosine. How can I get everything in terms of x? Well, remember, x is actually equal to sine of y, and cosine and sine are related by the equation sine squared plus cosine squared equals 1. So I can rewrite this cosine of y as plus or minus the square root of a 1 minus sine squared x, or sine squared y, excuse me. And sine of y is x, so this is 1 minus x squared. And you say, okay, what was our implied domain for that arc sine function? Well, our implied domain, or our, excuse me, not our domain, our range for the arc sine function was negative pi over 2 to pi over 2. So we're always interested in values, or the y values that come out of this are always in quadrants 1 or 4. In that quadrant, in those two quadrants, quadrants 1 and 4, cosine is always positive. So we don't need the plus and the minus. We just need the positive square root because we're in quadrants 1 or 4. So we get that answer right there. Now, similarly, if I want the derivative of arc cosine of x with respect to x, I just take 1 and I divide by the derivative of cosine of y with respect to y. Here, our cosine of x equals y if x equals cosine of y. So this is actually x. We're taking its derivative with respect to y. The derivative of cosine is negative sine. And I'll put that negative 1 in the numerator. And you say, how do I relate that back to cosine? Well, using the same formula, sine squared plus cosine squared is 1. So we have negative 1 divided by plus or minus the square root of 1 minus cosine squared y. And if cosine of y is x, this is negative 1 divided by plus or minus the square root of 1 minus x squared. So what about that plus or minus? Let's think about sine of y. What was our range of values for arc cosine? Our range was 0 to pi because we restricted our cosine graph to the interval from 0 to pi to come up with that arc cosine graph to begin with. On the interval from 0 to pi, sine is always positive, so we don't need the plus or minus. And we find that the derivative of arc cosine is this negative 1 divided by the square root of 1 minus x squared. You see the same thing for arc sine. They're almost identical, except the arc cosine has a negative 1 factor. The arc sine does not have the negative 1 factor. Similarly, if I want the derivative of arc tangent of x with respect to x, that's 1 divided by the derivative with respect to y of tangent of y. The derivative of tangent of y is secant squared y. And say, okay, well, what is secant squared in terms of tangent squared? Well, secant squared is 1 plus tangent squared. And if tangent of y is x, this is 1 over 1 plus x squared. So that is the derivative of arc tangent. The derivative of arc cotangent with respect to x is 1 divided by the derivative with respect to y of cotangent of y. The derivative of cotangent of y is negative 1. cosecant squared y, putting that -1 in the numerator. And you say, well, how is cosecant squared y related to cotangent of y? Well, we know that cotangent of 1 plus cotangent squared y equals cosecant squared y. We just take that sine squared plus cosine squared equals 1 identity and divide everything by sine squared to get that new identity. Say, okay, well, if cotangent of y equals x, this is -1 over 1 plus x squared. So we see the derivative of arctangent and arccotangent are the same, except this sign is negative. The derivative of arc cosine has a -1 factor. The derivative of arc cotangent has a -1 factor. And we'll see that the derivatives of arc secant and arc cosecant are the same, except the arc cosecant function will have a -1 factor. So it's really, sometimes students think it's like memorizing a lot of rules. It's really not. It's mostly memorizing 3 rules: the derivatives of arc sine, arc tangent, and arc secant. And hopefully you actually understand where they come from, so you could derive them every time if you wanted to. But if you remember the derivative of arc sine, arc tangent, and arc cosecant, or arc sine, arc tangent, and arc secant, and then can remember that the arc cofunctions all are identical to their sort of corresponding function, but with a -1 factor on top, then you'll see that then it won't be too bad. You won't be memorizing 6 new rules. You'll basically be remembering 3 new rules with some sort of fine print to get the other 6 or the other 3 derivatives of inverse trig function. All right, so now we are almost done with this. The last one is the derivative of arc secant. This one is a little trickier. Got 1 over the derivative with respect to y of secant of y, where secant of y is equal to x. And the derivative of secant of y with respect to y is secant of y times tangent of y. And we want that in terms of secant of y only. So we say, okay, well, what is tangent of y in terms of secant of y? Well, 1 plus tangent squared equals secant squared. So this is going to be secant of y times tangent of y, which is plus or minus the square root of secant squared y minus 1. That ends up being 1 divided by plus or minus x times the square root of x squared minus 1. Now, x squared minus 1 is always positive, and this plus or minus x, you might wonder, which one is it? Is it positive x or negative x? Is it the absolute value of x? What is it? It turns out to be the absolute value of x. But we can see that it's the absolute value if we look at the arcsecant graph, and we just looked at that in the last video. It comes from taking our cosine graph, thinking about when the cosine is 0, so at all the odd multiples of pi over 2, and then evaluating the secant at the top of all of those functions and the bottom of all of those functions, that relative minima and relative max and relative min. And then thinking about what happens as we divide by a small positive number, then the function goes to infinity, and divide by a small negative number, the function goes to negative infinity. This is the restricted secant graph. So we're on the interval from 0 to pi. And if we're on, if we're looking at the tangent graph at the same time, the tangent looks like this. Tangent has asymptotes at all the odd multiples of negative pi, or of pi over 2 as well. A little bit hard to see because I've drawn the tangent graph a little bit wider. This is what secant looks like, and this is what tangent looks like. That derivative of secant, or that derivative in the denominator, secant of y times tangent of y. I'd say, okay, well, what is the sign of that supposed to be? Well, on the interval from when y is between 0 and pi over 2, we've got a positive number for our secant times a positive number for our tangent. So it's going to be a positive times a positive, which is positive. And then on this interval from pi over 2 to pi, secant is negative and tangent is negative. So we're going to have a negative times a negative, which is positive. So this derivative in the denominator needs to be positive all the time. Now, secant is positive on this interval, the interval from 0 to pi over 2, and negative on the interval from pi over 2 to pi. But we don't want that. We want just the positive answer. In order to get the positive answer, we just take the absolute value of that. Plus or minus x could also be written as the absolute value of x. And that turns out to be the derivative of arcsecant. I hope that makes sense. Again, you're saying, how do you know that that's got to be absolute value of x? Because we're looking at the SIGN sign of secant of y times tangent of y by looking at the y values on the secant graph between 0 and pi over 2, and the corresponding y values on the tangent graph. Positive times a positive is positive. That makes this positive. Or looking at the y values on the next interval, we've got a negative for our secant values and a negative for our tangent values. A negative times a negative should be a positive answer as well. So we should get a positive answer from that secant of y. So that's why we need to take its absolute value. And that square root is always going to give us a positive answer. Okay, so that's arcsecant, derivative of arcsecant. Arccosecant is similar. It's 1 over the derivative with respect to y of x. Well, x is cosecant of y. And the derivative of cosecant of y is negative cosecant of y, cotangent of y. And we want everything in terms of cosecant of y. Cotangent of y is actually, well, we know 1 plus cotangent squared equals cosecant squared. So this is going to be negative cosecant of y times plus or minus the square root of cosecant squared y minus 1. And you say, okay, can I put an absolute value out here like we did in the last one? Well, a couple of things that we need to keep in mind. Our cosecant is well defined for, or gives us values between negative pi over 2 and pi over 2. So we're interested in the sign of these two factors on the interval from negative pi over 2 to pi over 2. We use the same restriction that we use for sine with our cosecant, because cosecant is 1 divided by sine. So we're interested in negative pi over 2 to pi over 2. And we know sine looks like this. Now cosecant looks like this. And we're interested in it between negative pi over 2 and pi over 2. So we're just interested in this particular part. All right, so on the interval from negative pi over 2 to 0, cosecant is negative, and from the interval from 0 to pi over 2, cosecant is positive. My goal is for it to find out the SIGN sign of this expression in the denominator. So I'm looking at that cosecant times cotangent. You say, okay, well, what does cosecant, or that's what cosecant looks like. What does cotangent look like? Let's graph that. Cotangent is undefined whenever sine is 0. So at negative pi, 0, pi, all the multiples of pi are our cotangent has asymptotes. Cotangent is cosine of x divided by sine of x. And it decreases, looks like this. And it crosses the x-axis at negative pi over 2 here and pi over 2 there. And again, we're only interested in part of the graph. We're interested in the part between negative pi over 2 and pi over 2. So we're going to look at this part and then this part. You say, okay, on the interval from negative pi over 2 to pi over 2, I'm taking cosecant and I'm multiplying by cotangent. I've got a negative times a negative, which is a positive. So this is a positive times an extra negative 1. So it's definitely negative. Then on this interval from 0 to pi over 2, I've got a positive times a positive. So I have a positive times that negative sign. So it's definitely negative. So this negative I can bring up to the numerator. That's going to give me negative 1 divided by plus or minus cosecant of y times the square root of cosecant squared y minus 1. Since the answer is supposed to be positive in the denominator, we factored that negative 1 out. We put it in the numerator. I'm going to take the absolute value of that. It's plus or minus cosecant of y is the same as the absolute value of cosecant of y. And cosecant of y equals x. This is negative 1 divided by the absolute value of x times x square root of x squared minus 1. Notice again that the derivative of our cosecant and our secant are the same, except the arc cosecant has a negative 1 in the numerator. All right, so those are all of our derivative rules. Now that we've reviewed our derivative rules and reviewed where they come from this identity that we discussed when we discussed inverse functions. And we can apply these in various application problems. So we'll look at finding relative extrema, finding points of inflection, graphing problems, and also some application problems. I usually solve those application problems as related rates problems, but they can also often be solved in terms of inverse trig functions. So it'll give us a good opportunity to practice using these rules that we've just derived.